I'm Chai from Cruise. And first, I'd like to thank the organizers for giving me the opportunity to speak on behalf of our company. I'm truly humbled to be here to speak alongside so many pioneers in the self-driving and robotics industry. So yeah, let's get started. For those of you who don't know, we are Cruise. We are a self-driving car startup based in San Francisco, and we specialize in building a self-driving car fleet for ride-hailing and delivery services. So today, you've heard a lot about self-driving and self-driving car companies. So how are we different from all the other ones you heard about from today? So actually last year, we achieved quite a milestone. We were the first to operate a driverless fleet in dense urban city in the US. And so far, we are the only one with a permit to charge customers for driverless rides in San Francisco. And I know that the word driverless or self-driving or autonomous vehicle or full self-driving have been thrown around a lot. So just let me clarify what we mean by driverless. So as you can see on the right hand on this picture, let me get my laser pointer. So it's really nobody sitting in the car. So we don't have a safety driver. We don't have a passenger side driver. We don't have a leading car. We don't have a following car. And our customers are not liable to damages when in unlikely events, right? So that's the main difference between driverless and not driverless. And we are doing it at a scale in San Francisco. So, and we also invited members of the general public to take our rides. If you search on YouTube, there are videos from us, but there are also videos from individuals who are unrelated to Cruise who have uploaded videos of their rides. Now, we've taken a fairly measured rollout approach. So towards the end of last year, we started with 2 cars covering roughly 30% of San Francisco, and we only drove in late night. And as of May this year, we scaled up to tens of cars covering 70% of San Francisco, and we greatly expanded the hours we have our driverless operation as well. And as you can see, that if you further project the trajectory, soon we'll be able to have hundreds of cars driving 100% of San Francisco 24/7. So you are not here to hear me say, okay, the driverless problem is solved. I will echo Philip Cranbu's point earlier. So there are still a lot of challenges for you and me to solve. So what are they? So ultimately, it's all about scaling. So one is scaling in San Francisco. This is a place that we know well, but there are, this safety is something we and smoother journeys. That's where we can always make more improvements. So essentially, we see that for years to come, once we even have a 100% coverage in San Francisco, for the years to come, we'll keep making improvements. And we need to handle more complex situations. We need to perform more sophisticated maneuvers. So here is a demonstration. This is just in simulation. It's not something we do today. But imagine we have hundreds of those cars, and they need to park quickly, right? So this is, for example, somewhat a superhuman maneuver, because if you have a lot of cars, you don't want them to park at the same time. But because we have control over this car, this is a maneuver that we can potentially do. So scale now, next is scaling to new locations. So this is more like scaling in the traditional sense. There are new countries, new cities, people driving on the left-hand side, different weather conditions. There's also new landscapes like dense city versus suburbs versus rural areas. And you can say that dense city is a lot harder than rural areas, but rural areas that pose other challenges like mapping is less efficient, for example, because you have to drive a lot to get your map. I think somebody mentioned about this before as well. It's about scaling to new platforms. So at Cruise, we have our Bolt car. So this is this Bolt car. And we also have next generation Origin car that you might be able to, might find this vehicle at our booth later this week. So our hardware engineers are still tirelessly working on more efficient sensors and less costly hardware. And we need a software stack that can generalize across all these different platforms. So let me summarize. So we have these 3 corners of opportunities in terms of scaling. And what are all the things we can do? So this is just a small subset. I think a lot of things here have been talked about over the course of today and at other workshops and hopefully over the conference, main conference as well. So today I'll just deep dive into 5 of these areas. So some of them I will deep dive more, go deeper than the others. So the idea here is to tell you what we have been up to in terms of research and engineering, and hopefully give you some of these might inspire you. Kendall talked about this earlier as well. I'm really glad that he did. So basically, this is something that reinforcement learning, automatic mining and labeling, and I'll wrap up the talk. Epistemic uncertainty. So I'll make this example for the task of so the role is so this is post-perception. So the role is to given this top-down representation of the world, you want to predict where the agents are going to go. And just for clarity, I'll refer other road users as agents, and the ego car as a self-driving car or autonomous vehicle, or AV in short. So typically in the literature, you will then predict a mixture. For example, for this agent, you'll say, okay, this agent will 70% of the time will turn left, 25% will go straight, and 5% to the right. And for another agent, you'll say, okay, it's 100% going straight. And what is epistemic uncertainty? It's about knowing when the model doesn't know something. So I'll just start with a small game. So here is a scenario where you have an agent jumping out of his car and started running backwards. So now I want to give you 5 seconds to think about what will happen next. Right? Just put yourself in the shoes of a prediction model. So here is what really happened. So the agent exited the car and then tried to avoid this other car and then fell down on our lane. And yeah, fortunately, we were able to stop in time. So I'll play this video another time. So who of you have guessed the future correctly? Let me see. Oh, great. Excellent. Yeah, please join us to improve our prediction. So as you can see, this is a very long tail problem. So it's very difficult for a machine learned system to correctly predict what's going to happen. And that's what epistemic uncertainty is for. Sorry, I play this again. So in the literature, uncertainty can be estimated by a lot of things. For example, Bayesian networks or dropout. Again, Alex Kendall earlier talked about this. He's actually an expert in uncertainty estimation. But today we'll talk about estimating uncertainty using an ensemble. So I'll break this down a little bit as well. So we're deep in maths. So we see, so you have usually you have a training set that's denoted X training here. And it's now a stochastic function to get your model. So the weight W denotes model weights for the model itself. And you essentially draw N models from your ensemble, right? And now your prediction Y, given the input X, is now the expectation over your models. And just for simplicity, I'll get rid of X here. It doesn't contribute too much. And the overall uncertainty is then defined as the entropy over Y. That makes sense, right? The uncertainty is what, you have your output Y, and the uncertainty is the entropy over this random variable. So now I want to talk a little bit about, what's, in this uncertainty, this overall uncertainty, you actually have 2 types of different uncertainties. You have the allele tree, you have the epistemic uncertainty. And especially for the task of prediction, it's very important that we distinguish between the 2 types. So, so you have on the top left here, you have a case of low uncertainty overall. So it's low epistemic or low allele tree. So you have 10 models, they are denoted by different colors, and they all predict the same direction with 100% confidence. So there's really nothing to see here. This is the model is really confident. There's no uncertainty. Now, the fun thing here is the difference between the top right figure and the bottom left figure. So they have more or less the same total uncertainty, but one of them has high epistemic but low allele tree, and the other one has low epistemic and high allele tree. So in this case, the top right case, you have 10 models. They are all very certain about what they are doing, but they all have different answers, right? So it's low in allele tree because they are all confident about this one prediction, but when you look at them as a whole, it's a high distribution over possible futures. But then you also have this high allele tree and low epistemic case where all your models actually agree with each other. They all predict 2 modes, and even within the modes. So the circles here are Gaussian circles. There is a the high lateral uncertainty within the 2 modes. So essentially, all your models agree. It's just there's just by intrinsically the problem of prediction, you are supposed to predict 2 different futures because maybe the pedestrian is at intersection, for example. But you also have the high epistemic, high allele tree case. It's essentially just chaos. The model cannot do anything here. It's not important. So the key here is that we need to isolate the epistemic uncertainty from the overall uncertainty. How do we do that? So we can define the epistemic uncertainty as a mutual information between Y and W. So you have your prediction Y, you have your weights W, and by definition, mutual information, you can split it. I mean, the definition makes sense because if Y is independent from W, there's basically no epistemic uncertainty, right? And now the mutual information can be split into, and just by definition of mutual information, it's entropy of Y subtract the conditional entropy of Y given W. And that now makes even more sense because as we saw before, the entropy of Y is the overall uncertainty, where the conditional entropy of Y given W is allele tree uncertainty. So what you see here is really that the overall uncertainty consists of the sum of allele tree and epistemic uncertainties. And now, allele tree uncertainty in the ensemble model is then defined like this. But unfortunately, none of these entropies are analytically solvable. And the only way we can solve it is to do a Monte Carlo estimate. And here I'm just showing you like how many Monte Carlo samples you need to draw for the task of prediction. So let's see just one example of this thing in action. So essentially, we trained a state-of-the-art predictor for pedestrians. And you can see that the pedestrian is walking along this black line here. And then we use our epistemic uncertainty estimator over the entire time period. And where we discover a peak here, this star here, is indeed at the so here you see a pedestrian going behind the car and then nonchalantly walks into the middle of the road, right? So here what we see is really that the model is the most uncertain. So the allele tree uncertainty, as you can see here, is mostly stable. And the model is really confused when the agent starts to walk into the road, where some of the models say, okay, this guy is going to go across the street, where the other model said, okay, this person is probably going to go alongside the car. So essentially, the model doesn't really know what's going to happen next. And this is exactly where you need the model to say, okay, I don't know. Planner, now be very gentle and very careful what you're going to do next. So much to uncertainties. The next topic is about radar, and it's not even a rebuttal of Tesla, who got rid of their radar. So this is more. So the comment here is really about radar is often overshadowed by LiDAR. So the LiDAR gives you range and azimuth. So radar gives you more or less the same thing, but at a lower quality and accuracy. So the point I want to make today is that there's actually still a lot of value in the radar. For one, it provides redundancy, but more critically, it provides you the sensor that you need for adverse weather conditions. And here are some examples. So on the left-hand side, you see an example of snow. So here we have a car in the snow, and you can see that the sensors are even covered in snow. It's really, really heavy snow. And in LiDAR, you basically have nothing. So there's in front is empty, right? But radar, on the other hand, is not affected by the snow at all. And here on the right-hand side, I have the example of San Francisco. And it's an actual case in San Francisco where we had some steam on the road, and in the camera view, there's nothing. There's actually a car here. You can see like really vaguely to the front light here, but the camera detector has no chance. So the LiDAR detector here doesn't see any points either, because the entire steam, it's basically this thing here. So this thing here is a steam, right? So the LiDAR can't see the agent neither. And it's very important because here you have the car coming, the car can turn left and where you need to stop, or you can be turning left. And if you don't see that car, it's very dangerous. So here, the same scenario. So if we had the radar as an input, the LiDAR doesn't detect anything where the radar can see this agent perfectly, right? So we have our proprietary radar technology that gives us 3D tensor as well, so azimuth, range, and Doppler. And they are a lot more accurate and dense than traditional sparse radars. So really the point I want to make today is that there are a lot of opportunities in research into radar. So I mean, just a simple search gave me 3 papers about radar at this conference, where LiDAR has 22, and if you search for point cloud, you have like hundreds. So here I'm just like a very simple example I have here is kind of a research that we've been doing is that we can compensate. So there's a Doppler component in the radar, and that measures, if you think it measures the speed of you with respect to other agents. And if you are actually driving, the Doppler channel actually doesn't give you 0, even if the other agents are stationary. And that's not something you want, but you understand your own speed and you understand the physics as well. And it's a very simple trick to compensate for the Doppler, for your own ego motion. So you can essentially bring the entire Doppler channel back to 0 for stationary objects. It's a very simple trick, but just to highlight the room of possibility in terms of research in this area. And here, just by doing this simple trick, right, we boosted our radar object detection performance by 9% and camera radar fusion by 3.5%. And it's not even a very difficult work. Now, next topic, I'd like to talk about adversarial reinforcement learning agents. The motivation here is there are a lot of aggressive and unpredictable road users that are critical, but are extremely rare to find. And the question is, how do we build a robust validation framework around them? So here on the bottom, I'm showing you a bicyclist who tries to avoid a car pulling out, but they directly walked, kind of rode into our line, right? It's not something I would have done. I would have probably stopped and jumped off my bike. And on the left-hand side, you have a pedestrian who lost her hat, and they just quickly turned around and then started moving backwards. So these examples are extremely rare. So if we only test our self-driving car stack against the ones that we find, we'll always find more of these cases. So how can we preemptively force these challenging scenarios to happen? And that's where we build adversarial RL agents. So when you think about reinforcement learning, it's very natural to be used for self-driving, right? You have, when you think about AlphaGo, when you think about all these successes in reinforcement learning, but there are 2 challenges preventing reinforcement learning being used very well for the self-driving car problem. First, you don't have a good simulator, because if you can simulate all the other agents, the problem is solved. Secondly, it's very difficult to define rewards. So you have to do a lot of rewards. So there are multiple factors, right? There are, you want to reduce number of fatalities, you want to reduce number of collisions, but at the same time, you don't want to be, slow, like if as walking, you don't want to drive at a walking speed, right? So in this work, essentially, we were able to make RL make sense by bypassing these 2 problems. So essentially, we said, okay, we want to train adversarial agents who seek to get hit by our car. And just making this very simple assumption, you can phrase this entire thing into a very well-defined RL problem, right? In the simulator, we have our self-driving car agents. We know what that is. We can run it. And you get the agents from for the other agents, you get it. That's something that you're training. So essentially your simulator has everything it needs to simulate something well. And now you can collect a bunch of replays and you can apply the simple PPO with a reward that says, okay, do I get hit and how hard do I get hit? So now we've trained basically an agent that is very adversarial to our specific self-driving car stack. And what are the fun things that we can do with it? So here I'm playing out a video where a jaywalker comes behind a car, and then nothing bad happened because we stopped. The other agent saw us and stopped as well, and the other agent didn't proceed until they realized that we have stopped. Right. So this is turned out good, turned out well. But now, how can we make this case more challenging for our self-driving car? So now we essentially, this is now all in simulation, as you can see. The other cars are still the same as before, but now this one agent, we made it adversarial. So now this agent doesn't even look at us, just actually accelerated and moved across the road. And fortunately, our car could still navigate well around that pedestrian. So I'll just play this video one more time. So this is essentially, instead of waiting for corner cases and long tail cases to happen and then ask ourselves how to fix them, we preemptively find challenging cases and solve them. All right. All right. So next topic, I want to talk about data. The key here is to learn from every mile driven. So we have hundreds of cars on the road. We collect really a lot of data, more data than we can actually train our models, even with auto labeling. Now, there's something that really resonated with me. I think Andrew Ning came out last year and said, okay, what we need is not big data. What we need is good and smart data. And that's where we basically invested more in learning automation. So we have this setup where we iterate automatically between driving on the road and mining for data and updating our models. And as you can imagine, a core component here is a trigger to say, okay, when is something interesting, right? Because after all, we cannot take all the data and train our models. So, initially we use signals from safety drivers as triggers, but as our self-driving car performed better and better, these kind of triggers became rare and rare. Then we started using, handcrafted features with similarity search, but a lot of times the precision is not that great, right? For example, here we had a trigger for, bikes U-turn, but it gave us a lot of, just simple left turns. It's no fun. So we made further improvements where we adopted kind of a few-shot active learning strategy to use machine learning to train all of our triggers. And now we can really find with high precision, these samples where a bike makes a sudden U-turn, and that we can then feed back to our modeling pipeline to improve our models. And finally, the last thing I want to talk about is when you want to scale, you need to iterate fast. And that's why we also invest heavily in tooling automation. And here is basically when you have a perfect model, now you want to productionize it. I think a lot of you have been there. Now you have to kind of prune the model, you have to quantize the model, and you have to kind of, all kinds of optimization things that you need to do. And you actually need to change your code to do that. And it's very cumbersome, right? And then next week, you have your new model, you have to do this process all over again. So our tooling, our infrastructure folks, they come up with a source-to-source compiler to translate, your perfect model to something that's deployable hardware, right? And it's essentially with a simple compiler flag, you can say, okay, I'll just train the original model, training eval export, or you can say, yeah, I want to include pruning, right? Now I don't need to change any of my code, it's source code, and the compiler will give you a pruned model. And if you can say, okay, I want it to be quantized as well, you can do it again with a simple compiler flag. And you can do even more complicated things like pruning first and train and then quantize and eval and export. So it's very important in the age where you need to iterate fast, you need to scale. It's very important that infrastructure catches up with the advance we have in general machine learning. All right, so in summary, today I highlighted the challenges in deploying and scaling up an autonomous driving fleet. I deep dive into epistemic uncertainty, into radar, into adversarial RL agents, and model training automation, and model optimization automation. And this only represents a fraction of the work, the research and engineering work we do at Cruise today. So if you're interested in our company, please drop by at booth 1001. It's a great number. We'd be happy to have a chat.